Good afternoon, everyone. I think we will just wait for a couple of more minutes, and I think then we can start. I think we should start. So, hi everyone. Welcome to the live session 4 of the course Digital Circuits. The course is taught by Professor Shantanu Chakraborty from IIT Kharagpur. I am Mr. Rafiq. I am from Department of Electrical Engineering at IIT Kanpur. I am a PhD student. Basically, I am a PMR scholar. So, we carry out this NPTEL TA work as a part of our PMR duties. So every live session we discuss some problems pertaining to the assignments, not exactly the assignment problems, but in the same, like sharing the same concept or difficulty level, so that you'll be very well versed with these problems and you can solve your assignments and hopefully that will help you in your exams. So today we'll be discussing problems more precisely from week 4 material. So how I proceed in my lecture is that I show a problem and its solution as well. And also I give some problems for students to solve first. Once they solve the problem, I ask them to type in the correct option in the chat box. And then I also show the solution to them. So this is how I usually operate. And one more thing, please turn off your microphones and switch off your cameras. Only turn on your microphones when needed, when you have some doubt. Try to write your doubts in chat box. If not possible, you can unmute that time. That's all. Actually, we are bound to give this introduction, these rules every time we hold a live session. So that's why I have to repeat it again and again. So coming to the first problem of today's live session, that is live session number 4 of course digital circuits. It states that, just a second, let me put the correct pen here. Yeah. So the question is the output Y of the logic circuit given below is, so we are given this logic circuit and we need to figure out its output. It's pretty simple. I'll just show you the steps. First of all, let's identify each gate. Right. Here, this gate is simply a NOT gate. Right. NOT gate. And this right here, this is your exclusive OR. That is XOR gate. We sometimes call it XOR gate. Now, what we have here is we have input that is X bar. That means X complement. That goes to one of the inputs of XOR gate. Right. And its another input is the complement of X bar. So here this will be X bar bar, that is simply equal to X, and this is Y. So Y will simply be equal to X bar, right? X. And how do we write exclusive OR? We just make a circle and inside that we place the plus sign. So this is the operation that this logic gate carries out here, and this will be equal to, we can take help of the truth table as well. So the truth table of XOR gate I am drawing here. So 0 0 0 1 1 0 1 1. It will be 0, 1, 1, 0. So XOR is always high when both the inputs are different. And right now what we have here is we have X and X bar. So X and X bar are always opposite of each other, right? So my output will always be high. So what I did here is the functionality this Y is performing is exclusive OR operation between the input I and its complement signal, that is X bar, right? And X and X bar are always different. If X is 1, X bar is 0. If X is 0, X bar is 1. So that implies their exclusive OR operation will always give me an output that is high. That is Y is equal to 1. So the correct answer to this question will be option A, Y equal to 1. Correct? Any doubts? If not, I think we can proceed to the next problem of today's live session. That is, a CMOS inverter circuit has a pair of transistors which are A, 2 PMOS, B, 2 BJTs, C, 2 NMOS, and D, 2 complementary CMOS. So can anyone give me the right answer in the chat box? What is the answer to this question? Anyone? What will be the answer to this question? The question reads as CMOS inverter circuit has a pair of transistors which are 2 PMOS, 2 BJTs, 2 NMOS, 2 complementary CMOS. Am I audible by the way? Am I audible? Can please anyone confirm? Okay, so I am audible. So what will be the answer to this question? Anyone? Hey, it's easy. Come on. Yeah, finally, I finally have an answer. Yeah, Rohit, it's right. Option D is the correct answer. So let me just elaborate on the CMOS inverter part. So how do we construct a CMOS inverter? Basically, C stands for complementary, and M stands for metal oxide semiconductor. Basically, this is the structure of transistor, metal oxide semiconductor field effect transistor. We call it MOSFET. So what we have here is we have a PMOS and a NMOS. Basically, P type MOSFET and a M type MOSFET. And right here, this is your V in, this is your output, this is right here is VDD. I'll just spend some time here because I want to give some perspective of this. First of all, let me just correct it. First of all, this is the schematic of a CMOS inverter. A question to you guys: is this correct? Have I drawn it correct? Yes or no? Have I drawn it correctly? So can you point out what is the error? Correct. Yeah, bubble, which is a PMOS. Yeah, you need to be careful with that. So what I am missing here is was this bubble that represents a PMOS. Correct. So this is a simple CMOS inverter. Basically, how it works is operation is when your input is 0, that means low, my output will be 1, and my when my input is 1, my output will be 0. So at any point of time, only one of the transistor is on during steady state and other is off. So when input is low, I have PMOS on and this V0 is pulled up to VDD. And when Vin is 0, this V0 is connected to ground, and as a result, my output, that is V0, is 0. I have a question here, first of all. So I have a question for you guys here. So this is 1, 2, 3. What have I drawn here? Can anyone tell me what is this? What I have drawn here? So let me repeat. I have drawn this structure. What is this? Come on, you guys know. I just said it. I'm no, not PMOS. It's NMOS, right? I haven't placed any bubble there, right? If there was a bubble, it would have been a PMOS. So everyone is with me. It's an NMOS, right? Now I have a question for you guys. What is 2, what is 1, and what is 3? Which terminal is 2, which terminal is 1, and which terminal is 3? Actually, there is a fourth terminal also, but I haven't shown it here. Let's just concentrate on 3 terminals first. So what is 1, what is 2, and what is 3? You can use your microphones as well if you are not having, if you are not comfortable with chat box. You can unmute yourself. So what is 1, what is 2, and what is 3? Anyone else? Anyone else? So let me just tell you, 2 is gate. That's for sure. 2 is gate. I don't debate with that. I don't have any problem with that. But let me just ask you another question. Uh, how do you know 1 is source or 1 is drain or 3 is the source or 3 is drain? How do you know? What was the logic behind it? Picking 1 source or drain or 3 source or drain? What was the logic behind it? I'll tell you one thing here. Keep this thing in mind forever. MOSFET is a symmetric structure. You can interchange source and drain. So what defines a source or a drain in an NMOS is the potential, basically, to which it's connected. If a high potential is given to one of the terminals, it's termed as drain, and the other one is termed as source. So it is your voltage that determines your source and drain terminal in a MOSFET. So if this is my NMOS, this is my gate. If I connect VDD to here, this becomes my drain, and this becomes my source if I ground it. Keep this thing in mind always. And what about PMOS? PMOS, it becomes slightly opposite. So PMOS, okay, let's stop there. What is this terminal? This terminal, what is this terminal that I have highlighted? This, what is this? Yes, this is source. This is source of a PMOS. So in PMOS, the source is connected to the higher potential. So that is, it will be connected to VDD. Ground can be connected to some lower potential or it will be grounded. sorry, drain can be grounded or it will contain some lower potential. So we can interchange. If I put VDD here and ground here, then this becomes my drain and this becomes my source. Why drain? Because source supplies the electrons and they are collected by drain, and as a result, current flows from drain to source because the current direction is opposite to the that of motion of electrons. So this was this point. Now I'll come to another point in this topic here is why have we connected NMOS at the bottom and PMOS at the top? Why? Why NMOS? Why is NMOS connected at the bottom and PMOS at the top? What is the logic behind it? So this is CMOS inverter we established, and it's made up of a PMOS and NMOS, where PMOS is connected to here and NMOS at the bottom. Then I showed you that in MOSFET the source drain are different based on the voltages applied to them. If in NMOS, if terminal is having a higher voltage, it's drain, and the other terminal is source. But now my question is why we connect PMOS at the top and NMOS at the bottom? What is the logic behind it? So the answer is I want you guys to look into it. I won't go into the details here. What NMOS is, I'll just give you some keywords. NMOS passes passes strong 0 and PMOS passes strong 1. This is your key. Do search about it and you will get your answers. NMOS passes strong 0, PMOS passes strong 1. This is your kind of a hint to your answer. I want you guys to look into this. Why CMOS, why PMOS is at top and NMOS is at the bottom. So this was some kind of an overview to this CMOS inverter. This is an extremely important concept, this CMOS inverter. When we talk about digital integrated circuits, we usually do it in digital integrated circuits course. That is another course. I think I don't know whether that's floating this semester in here in an NPTEL. And usually we do it in PG and even some UG guys also do it in some institutes. So if you want more perspective about digital integrated circuits, you can refer to lectures from Professor Janki Raman of IIT Madras, and also you can refer to the book by Digital Integrated Circuits by Professor Janam Rabai from UCB. So extremely important topic from a digital circuits point of view. It's once you finish this digital circuits course that you are right now doing, then you switch to this digital integrated circuits. But this requires some at least what should I say, prerequisite is basic knowledge of electron devices. Not that much, but some basic knowledge. It's mostly a PG course, but even some institute is short in UG. It's kind of some institute do it in UG, some institute do it in PG. But it's a really important course, nice course. Now, question number 3, I want you guys to do first, then I'll show you the solution. The question 3 states that how many two input AND gates and how two input OR gates are required to realize y equal to BD plus CE plus AB. So I'm giving this function y equal to BD plus CE plus AB, and the question asks us how many two input AND gates and two input OR gates are required. Anyone? I'll give you a couple of minutes. You can type your answer. Yeah, anyone? Yeah, yeah. Please type your answers. Should not take much time. Correct. So this is pretty simple. The answer to this question is option A, that is 3 comma 2. 3 AND gates and 2 OR gates. So how? Basically the functionality that we are required to perform is y equal to bd plus ce plus ab, right? And what is this? This is an AND operation. This is an AND operation. This is an AND operation. So I require three two input AND operations. So I'll be needing three two input gates. And then they are odd. So or. So two OR operations. So I'll be requiring two input OR gates. So my answer is 3 and 2 OR, option A. Now we have another question that states the logic functionality realized by the circuit shown below is. So we are given this circuit and we are required to show the functionality performed by the logic circuit. Now I have a question for you guys. Which gate is this? I mean to say, which transistors are these? What are these transistors? Are these PMOS or NMOS? Yeah, NMOS. Thank you so much. They are NMOS transistors, and we are required to perform the functionality. What functionality? We are required to find the functionality performed by them. So let me just redraw the circuit here. I have this. So this B is at the gate, A is here, and then we have Y, another NMOS transistor having input as B complement. Mind this complement here, and this here is, what does this represent? Anyone? What does this represent? Ground. And in digital circuits, what does ground correspond to in terms of digital signals? Correct. So ground corresponds to 0. Now let's do a step-by-step approach first. So I'll write A and A equal to 0, because two inputs are there, four cases will arise. A equal to 0, that is ground, and A equal to, sorry, B equal to 0, that is again ground. So when A equal to 0 and B equal to 0, and let me just term these as 1 and 2. So when A is equal to 0 and B equal to 0, what will happen to my transistor 1? Will it be on or off? Transistor 1, T1. Will transistor 1 be on or off? Anyone? Is my transistor 1 on or off when A equal to 0 and B equal to 0? Yes, it's off. And what about T2? It is on or off? On, correct. And as a result, my Y will be connected to this ground through path. And what will be my Y equal to then? Correct. Others, please also join in. Not only one student's answer, others should also part in. Then I have my second case, A equal to 0, that is again ground, and B equal to 1, that is VDD, that is the supply voltage. So again I am going to ask you, is my T1 on or off now when A equal to 0 and B equal to 1? Is T1 on or off? Yes, T1 is on and T2 will be off. And now I have path like this to A, connecting this Y to A, but A is ground, so my Y will be, so my Y will be My transistor 1 is on, transistor 2 is off, and A is at 0. Now my Y will be 0, correct. Similarly, we have another case A equal to 1, that is VDD, and B equal to 0. For that, we have T1 is off, T2 is on, and as a result, my Y is 0. And final case will be A equal to 1, that is VDD, B equal to 1, that is VDD, and my Y will be equal to this in this case. Okay, before going to Y, what will be my T1? Is T1 on or off? T1 is on, and here, what about T2? Correct, T2 is off. And as a result, I have a path to this connected to A, and then this Y will be pulled to VDD. That means Y is equal to 1. So after 4 cases, someone is using companion mode. Kindly stop it. So I don't know what difference does it make. Anyways, so the 4 cases that I have here is Y A equal to 0, B equal to 0. So for 0 0 I have 0. For this I have 0. For this I have 0, and ultimately I have 1. So which gate is this? So that this truth table corresponds to which gate? Yeah, this is AND gate. So for that you need to understand some basic of NMOS transistors. So let me just draw this. This is your NMOS transistor. Let's just connect for a moment this to ground, and this is A, and this is B. NMOS screen not visible. Can anyone confirm is screen visible or not? I think it should be visible. Yeah, it's visible. So I have so this is your NMOS transistor. Now what happens? This transistor, NMOS transistor, only turns on when voltage at B, this is gate voltage, is greater than some threshold voltage, VTN. This is usually some positive number. So what we say here is in digital, just for you, for the simplicity, just remember there are some other concepts involved, but for your simplicity, this is a transistor. It will turn on when input at gate is greater than threshold voltage, but in digital you just for a moment say when it's equal to high voltage. So high voltage will correspond to logic 1 or VDD here, and it will be off when it's 0, that is connected to ground. So it means it's basically a switch. When input B is 0, my transistor is off, and when input B is 1, my transistor is on. Basically it's the voltage, it should be, its voltage at the gate terminal should be greater than some threshold voltage. I won't dive into the operation details why it turns on after some particular voltage. It will require some basic knowledge about devices, electron devices, some concepts of accumulation, depletion, inversion, and once the channel forms, there is a conduction after we apply the drain voltage. So I won't go into that detail, but for you guys, for the simplicity, just remember transistor, NMOS transistor turns on when you apply a high voltage at the gate, right? Is that clear now? And for PMOS, it will be reverse. For PMOS transistor, my transistor is on if I apply a low voltage. Basically, ideally, what should be the case? We say VGS should be greater than VTN for NMOS. And for PMOS, I think we can say VGS should be less than VTP, where VTP is some negative number. No, no, it should be greater than. I think I messed up. Some convention details. So you can just, for simplicity, you can write mod of VGS should be greater than mod of VTP. That also makes sense. Yeah. Now, let's move forward to this next question of today's live session. It states that what is the major difference between half adders and full adders? So, anyone out of the options, what is the major difference between half adders and full adders? Yes, option C. Full adders, they have an input capability. So, full adders, we have operation A plus B plus Ci. We have a this. We have a capability, carry input capability. In half adder, we don't have a carry input capability. We have A, B, and my output is sum or carry. In full adder, my inputs are A, B, C, I, and my outputs are sorry, my outputs are sum and carry. So now I have this question for you guys to solve. I'll give you a couple of minutes. I think it should take more than 2 minutes. So I'll give you 3, 4 minutes. I'll just read this question for you. So this question states that, uh, just a second, I'll just turn on full screen. This question says that which of the following Boolean expressions correctly represents the relation between P, Q, R and M1. So you need to find out what is the relation between M1 and PQR. So I'll give you a couple of minutes. You can solve and type in your answer. Just type the option. No need to type the complete answer. Just type the option. Once you are done, I'll show you the solution then afterwards. I think I forgot to ask to Rohit. So Rohit, did you understand how transistor was on and off? How I considered them on and off? Okay, fair enough. Anyone else? Couple of students have written their answers. Anyone else? Okay, so I see people concurring with option D. Let's hope D is the correct answer. So for our simplicity, question itself I marked these outputs. So I'll request you guys always. I don't know how you do it, but once you have multiple gates in your circuit and you need to find the output, final output. Try to break these outputs that come in between. Like here, they have done X, Y, Z, and compute them and then do the final output. In that way, it becomes more precise and simple. So you don't have these big equations, some large number of variables to mess with. So in that way, it becomes compact, and in that way, you tend to make less mistakes. So what we have here is we have X, right? X is basically output of this gate. So this gate is NAND gate, this gate is OR gate, this is AND gate, and this here is XOR gate. So X is basically NAND operation between P and Q, and we represent by X is equal to PQ bar, right? Then I have Y. Y will be equal to OR operation between P and Q, right? We represent it like this, and R goes to this here. Now Z will be equal to X dot Y, right? That is here. This is the AND operation. So it will be equal to PQ bar and with P plus Q, right? And my final output Z will be equal to, sorry, M1. M1 will be equal to Z XOR with R. Now I have this Z. Z here. Let's simplify this Z. Using De Morgan's law, PQ bar will be equal to P bar plus Q bar, and I have P plus Q. So it is P bar P. P bar P is 0. Then it's P bar Q. Then it's P bar P. Then it's Q bar P, and then Q bar Q, that is 0. So this is P bar Q plus Q bar P. Can anyone tell me what is this? This is simply P XOR Q. So my Z will be equal to P XOR Q XOR R. So this is my final answer. M1 is equal to P XOR Q XOR with R. Option D, as pointed out by many of you. So I see someone sharing some Jamboard file. Let me just check it later. I don't know what is this. What is this is? Maybe I'll just open it later afterwards. Okay, is that fine with you? Rohit, is it something related to question or it's something else? I think we'll do it afterwards. Okay, okay, mistakenly. Okay, that's fine. No worries. Now I have this question. The delay times are measured between dash percentage levels of the input and output waveforms. What is the correct answer? I think all of you should know this. At what percentage levels of the output my delay is measured between input and output? Anyone? Anyone? What is the correct answer to this? Okay. The correct answer to this is 50%. The delay is measured between 50%. So let's say I have input signal here that was high initially and now it goes low and then it again goes to high, and then I have output signal. I'm making an exaggerated version out of it. Basically this signal was given to the input of an inverter. Sorry about that. So let's just assume this is 50% level. and this is 50% level of output. So this is defined as TPLH, that is propagation delay from low to high, and this is defined as propagation delay from high to low. Basically, output making a transition from low to high, and output making a transition from low to high to low. And the overall delay is then defined as TPHL plus TPLH divided by 2. These two points, these correspond to 50% level. So if my output was at VDD, this will be VDD by 2. These points are VDD by 2. That is at 50% level. When input is at 50% level and when output reaches to the 50% of its final output value, that is a max by 2, the delays between them is compared. So this is TPLH, TPHL, and the total propagation delay is given as the average of 2. Now we have this question on Hamming code. So I'll point out one thing here. Although I have kept this Hamming code, one of the Hamming code questions here, but I think in coming weeks, I don't exactly remember the week number. We will discuss Hamming code in detail, much more detail. But still, I have kept one question here. So we are given this 7-bit Hamming code which was received, that is 101101, and even parity is followed. But the received code was wrong. We need to figure out what was the correct code. So we are given this Hamming code following an even parity, and it is incorrect. Now we need to find the corrected code. So how will we do it? Let's just first mark these 7-bit Hamming code 4, 5, 6, 7. So this will be 1. Sorry, this will be 1, 1. Let me just correct it. This will be, pen is not working, strange. 1, just a second. This will be 1, 2, 3, 4, 5, 6, 7. Right. And we write this as P1 parity bit 1, P2 parity bit 2. This is my data bit 1, D1. This is my data bit parity bit 3. This is my P. This is my D2. This is my D3. This is my D4. So 4 data bits and 3 parity bits. Now we'll write the code that we received. So the code that we received was 101101, right? This was the code that we received given here. Now it follows an imparity. Let's just take parity 1 first. Parity 1. So 1 appears in which bit? 1 appears in 1, 3, bit position 1, bit position 3, bit position 5, and bit position 7. So it will be at 7 I have D4, at 5 I have D2, at 3 I have D1. Oh, I'm missing something. Yeah, D1. Yeah, and at P1 I have P1. So basically this will be, we need to check whether it follows in parity or not. So D4 is 1, D2 is 1, and D1 is 0, and P1 is 1. So total number of ones are 3. So it's odd, but it should have been even. So we'll write there as 1 because it's incorrect. So we'll mark 1 as incorrect. Mark incorrect using 1. Then I have P2, checking P2. P2 will appear in 2, 3, 2, bit number 2, bit number 3, bit number 5, because 5 is, no, 5 is 4 plus 1 and not in 5. 6, it will appear in 6. Bit number 6 and bit number 7. So P2 I have, for P2 I have to check D4, D3, D3, D1 and P2. So it will be D4 is 1, D4 is 1, D3 is 0, D1 is again 0, and P2 is 1. So it follows in parity, so I write 0 because there is no error. Then similarly for P3, actually I should write P4. Here it's P4 rather than writing P3. P4. So for P4 I have to check D4, D3, P2 and P4. Sorry, D2. D2 and P4. So it is 1011. So three ones are there. It's odd. So it will be again error. So now I have coming out with this. So error will be at position P4, P2, P1. What is P4, P2, P1? It's 101, and its decimal equivalent is 5. That implies error is at fifth bit. Fifth bit is this. So that implies D2 should be 0. That is the corrected code. And my corrected code then will be equal to, if D2 is 0, my corrected code will be equal to 1001 1001 That is option D. So option D is my correct answer. So what I did here is I first wrote the 7-bit code, marked all its position, the parities and data bit position. Then I checked each parity bit. So P1 I checked was giving me error. P4 I checked was giving me error. P2 was not giving me an error. So from that I concluded my error is at 101 position, that is bit number 5. Bit number 5 is data bit 2. That was 1 in the received code, but it will be 0 in the corrected code. So my corrected code will be 1001011. So option D is the right answer. Any doubts in here? I'll just again tell you, we'll discuss Hamming codes in much more detail in the coming weeks. But since I wanted to give you a flavor of it, I've just kept one question here as well. So coming to the question number 9 of today's live session, I have marked it in green. That means I want you guys to do it first, and then I'll show you the solution. The question reads as, in the circuit shown, what is y equal to? So the circuit given here is this, and you need to figure out what will be the output y equal to. Do it. I'll give you a couple of minutes, 2-3 minutes. You can type in your answer. Just type the options. No need to try to complete answer, and then I'll show the solution. So anyone else? Only one student has written answer so far. I guess this is a long weekend, holiday weekend for you guys. So that's why I assume this laziness. Anyways, I'll just wait for one more minute. So always remember CMOS, it gives answer in complementary form, right? Don't forget this complementary. So my Y is basically this and with this and then the complement because it's a CMOS logic. So this A, B, when they are in parallel in NMOS pull down network, it becomes an OR operation. It becomes A plus B, and then this right here is in series with this, so it becomes an AND operation, A plus B plus C. But remember, the whole thing will be complemented, right? So it is Y equal to A plus B dot C complement. Using De Morgan's law, it will be A plus what should I say? It becomes A plus B complement dot C complement. Am I missing something? No, not at all. A plus B dot C whole complement. Then it becomes A complement dot B complement. Ah, this is plus. This is plus, yeah. Using De Morgan's law, this becomes plus. So it becomes A complement dot B complement plus C complement. So option A is the correct answer. One thing I want to point out here is this thing in a CMOS block is called a pull-up network, which is made up of PMOS transistors, and this right here is your pull-down network. Again, I'll come to that point that I made earlier in CMOS inverters. When I discussed CMOS inverters, I asked you why pull-down network is made up of NMOS and why pull-up network is made up of PMOS. I want you guys to look into it and get the correct answer. I also gave you the hint regarding passing of strong 0 and V strong 1. This pull-up network and pull-down network, they are dual of each other. So what is dual? Basically, whatever appears in series in pull-down network will appear in parallel in pull-up network or vice versa. So you see A and B are in parallel here. They will appear in series in pull-up network. And C is series with this block. C will appear in parallel with this block. So this is some insights I wanted to give you guys. Now I have this question for you guys. So I'll solve it simultaneously. You can also do it at your place. So we have this question which says that find the Boolean expression from the logic diagram. So we are given this logic diagram and we need to find the Boolean expression from it. If possible, simplify it. So once we have the expression, we want to simplify it and then make the logic diagram of the simplified expression. So here we have the figure. Let's just mark each of the gates. So this right here is a NOT gate, right? This right here is an AND gate. This again is a NOT gate. This I think is an NOR gate. Yeah. This is a OR gate, and finally at the output I have AND gate. So I need to find out what D is equal to. So here I have input A that is going to the input of NOT gate. So this will be A complement This C is going to the input of NOT gate, so this will be C complement. And here A is coming here, and here this C is coming here, so it's C. Now let me just mark these x1, x2, x3, x4, right? So x1 will be simply equal to A bar B. Am I right? Yeah. X will be equal to A bar B. Then I have, what should I say? X2. X2 is simply C bar. No need to write X2. Anyways, I put C, X2 is there. So X2 will be equal to C bar. And then I have X3, which is the output of an OR gate between A and C. So it will be A plus C. Then I have X4, right? So X4 will be equal to X1 NOR with X2. So how do I represent NOR? X1 plus X2 whole bar. So this will be equal to, so what is X4? X1, what is X1? So X1 is A bar B, right? Plus X2. X2 is your C bar and its whole bar. Now what we'll do, we'll apply De Morgan's law. So it is A bar B dot C bar, A bar B whole bar dot C bar, right? Again applying De Morgan's law, it will be equal to A plus B bar dot C. So that implies it is equal to AC plus B bar C. So this is my X4. But my output is what? My output D is equal to X4 and with X3, right? So what is my X4? If I look here, plug it into here. So it is AC plus B bar C. And my X3, what is my X3? X3 is my A plus C. Now I have AC dot A. AC dot A will be simply AC. Then AC dot C will be equal to AC. Then B bar C and with A will be A B bar C. And finally I have B bar C. Basically B bar C dot C is simply B bar C. Let me write it here. A bar A B dot A is equal to AB for to avoid confusions. We know. Now AC plus AC, A plus A. So A plus A is equal to A is AC plus A B bar C plus B bar C. Let's just write AC here and B bar C common, so it will be 1 plus A. What is 1 plus A? 1 plus A is 1. So it is AC plus B bar C. Taking C common, so it is C A plus B bar, right? I see one of the students have done it correctly. Now this is our final simplified expression. This one. And if I want to implement it using the logic gate, what I will do here is I will have input signal C, I will have input signal A, and I have B that goes to the NOT gate first to do this B bar operation, and then this goes to XOR gate, sorry, OR gate, not XOR gate, and then these two will go to the AND gate. So this is my simplified picture. Any doubts in here? If not, we can proceed to the next question. I'll want you guys to do first, then I will show the solution to it. It should not take more than 1 minute. So the question reads as, given is a pull down network, find pull up network and also the logic function implemented. So obviously you can't write the pull down network in the chat box here and you cannot draw it, that's for sure. But I want you guys to do it at your place right now to draw the pull up network to this pull down network. so that we can create a complementary logic, CMOS logic, and also you have to write the what is the logic functionality implemented by this circuit. So what I want you guys to do is type only the circuit functionality. I'm to say the logic function implemented by this pull down network. Type it in the chat box. I'll give you 2-3 minutes and draw the draw what should I say draw I forgot, draw the pull up network at your place and write the functionality. Only write the function implemented by this block in the chat box. So has anyone done it? Type. Yeah. So one of the student has done it. Yeah, you're correct. So y is equal to, so this, they are in series, so it will be AB, and this is in parallel with this, so it will be AB plus C, and whole thing will be complement. So it is y is equal to AB plus C whole bar. And pull up network, you construct pull up network by simply taking the dual of pull down network. So whatever is in series will be become parallel combination. So here I have VDD, then I have A, this right here is B, and this right here is C, and this is your Y. So this is my pull up network. Now I have this question for you guys. Uh, I'll give you 3 minutes to solve this. So this is a circuit that is shown, a diagram, circuit diagram is given, and you are required to find what will be F equal to. There are four options. Type the correct answer in the chat box. It should not take more than 3 minutes. Has anyone done it, or you guys are still doing it? I see one answer in the chat box. What about others? Anyone else? So let me just show the solution. So I think I gave you ample time. So I have one more answer from student. So right. So let's just mark each of the output as x1, x2, x3, x4. This will be x5, x6, and finally my f as it is. So my x1 will be equal to p plus q bar because it's an OR gate. Using De Morgan's law, it will be p bar q bar. Then x2 will be equal to q plus r whole complement, that is q bar dot r bar, right? Then I have x3, similarly that will be equal to p plus r whole bar, that is p bar dot r bar. And finally I have x4, that is between q and r, it will be q bar dot r bar. Now my x5, let me just write it here. My x5 will be equal to x1 plus x2 whole bar, that is p bar q bar plus q bar r bar whole bar. And let's take q bar common, so it will be p bar plus r bar whole bar, so it will be q bar whole bar plus p bar plus r bar whole bar, so it will be p q plus p bar bar r bar bar, so it will be q plus pr. Similarly x6 will be equal to x3 plus x4 whole bar, that is p bar r bar plus q bar r bar whole bar. Taking r bar common, inside I have p bar plus q bar, then whole bar, that is r bar bar, p bar plus q bar whole bar, so it will be r plus pq. You can save your time by just looking at the similarity between two structures, two circuits. So it is r plus pq, right? My x6 is r plus pq and my x5 is q plus pr. Now my f is equal to x5 plus x6 whole bar, that is equal to q plus pr plus r plus pq, and whole thing is complemented. So it will be equal to q plus pr bar dot r plus pq bar using De Morgan's law. Then it will be again using De Morgan's law. I'll be having q bar dot P R bar, then I'll be having dot R bar dot PQ bar, right? Then what I'll do here is I'll again use De Morgan's law. I have Q bar P bar plus R bar dot R bar P bar plus Q bar. Then what I will do is I'll take this R bar kind of common and I will put it into this bracket R bar in this Q bar. It will be R bar P bar plus R bar, then P bar plus Q bar. So it will be equal to Q bar. If I take R bar common, it will be 1 plus P bar dot P bar plus Q bar. 1 plus P bar is simply 1, so it will be Q bar R bar dot P bar plus Q bar. Then I will take Q inside this bracket, so it will be R bar P bar Q bar plus Q bar. It will be equal to R bar, and Q bar, if I take common, it will be Q bar 1 plus P bar. So it will be R bar Q bar 1 plus P bar. It will be Q bar R bar, and ultimately it will be Q. If I use De Morgan's law, it will be Q plus R whole bar. That is option B, as rightly written by a couple of students. Any doubts in this question? If not, let's just proceed to question number 13 of today's live session. It states that consider the following circuit. The function of the above network is, so we need to find out the function of the above network. We have the NAND gates, we have the NOR gates, we have the AND gate, and we have the NOR gate again. So let me just mark the outputs. This will be A B bar. This will be C plus D bar. This will be E F. This will be A B bar plus E. Sorry, this will be A B bar dot E, and this will be E F dot C plus D whole bar. So what I did here is, this is the AND operation of A and B, so I have A B whole bar. This is a NOR operation between C and D, so it's C plus D. Let me just make it slightly big. So this is C plus D bar. This is AND operation between E and F, and this is then E. What I have done here. So this goes to, no, I think I made a mistake here. So this is F, and this is C plus D bar. So it's F dot C plus D whole bar, right? And then my X will be equal to this, this, and this NOR operation between them. So it will be A B bar dot E plus E F plus F dot C plus F dot C plus D bar, right? Where? Where I'm not able to see it. Let me just. Input is F dash. No, it's F. No, it's not F dash. It's F. It's F. Yeah, it's F. Treat it as F. Yeah. So this is. Let me just check it whether it is F or, yeah, it's F. A B bar dot E F C plus G bar. Yeah, it's F. Then I have this thing, and this is NOR, right? Then X will be equal to AB bar AB bar dot E whole bar plus EF dot EF bar dot F dot C plus D bar whole bar. So I use in De Morgan's law. Then I have X again using De Morgan's law. So it's AB bar bar plus E bar. Then it's E bar plus F bar. What I'm doing here is just using De Morgan's law. That's all. It's F bar plus C plus D bar bar. Right. And my expression then reduces to AB. Oh, what happened? Something happened. Okay. So this is. Oh, just give me a second. Give me a second. Yeah. So we were here. Just a second. So this will be C plus D. Be C plus D plus F. Now my expression gets reduced to AB plus E bar plus F bar, and this is C plus D plus F. So just doing some basic operations, it will be A B E bar plus A B F bar plus E bar dot E bar is E bar, and then it's E bar F bar, and then I have C plus D plus F. X will be equal to, taking E bar common, it will be AB plus F AB plus 1 plus F bar, and then it's AB F bar, and here it is C plus D plus F. This is bar D plus G plus F bar, then it's X. So 1 plus AB plus F bar is simply 1, so it will be E bar. So it is E bar plus AB F bar, and this is C plus D plus F bar. So I think I have the answer. So looking at the options, I can say it's E bar plus AB F bar dot C plus D plus F bar. So option B is the correct answer. This was a simple question. Just needed to be careful with the De Morgan's law, how we apply that, and taking some common terms out, and you have the reduced expression. Then I have question 14. The question 14 asks me to show the find the logic diagram for. So question 14 states that for logic operation, for following logic diagram, which expression is true. So there are some expressions and we need to figure out which expression is true. So what I will do here is I'll just write output of each of the terms. So first of all, this is and they are marked as it is. So here output of NOT gate will be A bar, output of NOT gate will be B bar. This right here is A and this right here is B. So then these two are ANDed, so it will be A bar dot B bar, and these two are ANDed, so it will be A dot B. Then I have my output X equal to A bar dot B bar dot AB whole bar. So it's A bar dot B bar dot AB whole bar. So option B is correct answer. So while I was solving this question, I found this question in one of the previous year assignments of this course or maybe some other course. I was wondering why this simple question is being put in this week 4 material. Maybe I came to this conclusion, I'm not sure. It basically is kind of the examiner wants to test your time management skills, your question reading skills. Basically, some people might go on solving this, trying to reduce it further. Maybe, I'm not sure. But always keep in mind, look at the options as well. So while I was doing this question, I first looked at the options and then I proceeded. And I had one thing in my mind that this option is in this question, so it's correct. What happens? Maybe some other students will go on solving, and they will not arrive at the correct answer as per the options. So it's always important to read question carefully and options carefully, then go to the solution. Don't just read the question and jump to the solution. Read options as well. I think that's a good practice that you should take care of. Then I have question number 15, which states that if a equal to 1, b equal to 1, what will be the values of y and z? So I have this not gate here. What happened to this? Not gate here or gate here. So this will be a bar, and we have this or operation. So it will be a plus b. So y will be equal to, this goes here. Y will be equal to a plus b dot a bar. So question asks us a equal to 1, that implies a bar equal to 0, that implies y equal to 0, right? Then my z is equal to y plus a plus b, and given here is b equal to 1, so it will be, and a is also equal to 1, y plus a plus 1, so it will be 1. So my y equal to 0 and z equal to 1 for a equal to b equal to 1. Y equal to 0, z equal to 1, option C. Option C is the correct answer. Now, this question I would like you guys to do first, and then I will show the solution. So the question asks us, in the circuit shown in the figure, if C equal to 0, the expression of Y is, so C equal to 0 is given, and you need to find out what will be the value of expression. Do it, I'll then show you the solution. It should not take more than 2 minutes. So I see one of the student has written the answer. Now let me just show the solution. So yeah, a couple of students have written. So the question asks us to find the output if C equal to 1. So C, I have this NOT gate. So this will be equal to C bar. This will be equal to A plus B whole bar, because the NOR gate is it. This is A B. Let me mark this as x1, this is x2. So x2 is equal to x1 dot ab. So it is a plus b whole bar dot ab. If I am not mistaken. Not, no, sorry. This is OR gate. I just wrote it. XOR. So x2 will be equal to x1 plus ab. So it is a plus b whole bar plus ab, and then y will be equal to x2 plus c bar, x2 plus c bar. Sorry, what I am doing. So y2 will be equal to x2 dot c bar whole bar. That implies y will be equal to x2 is a plus b bar plus ab dot c. Am I missing something? No, I don't think so. Or maybe. Yeah. I am missing x1. X1 I have written incorrect. So let me just do it again. So this here is c bar. This right here is a plus b whole bar. This right here is a plus b whole bar dot c. And this right here is ab. So my y will be equal to this thing x1 dot c whole bar, and x1 is equal to a plus b whole bar dot c plus ab. So my y will be equal to a plus b whole bar dot c plus ab dot c whole bar. So y will be equal to a plus b bar dot c whole bar dot ab dot a b bar. So I mean somewhere I'm making a mistake here. This is c bar. A plus b, a b. So a b plus a plus b bar plus c plus c. Okay, this is plus c. Here. Got it. So yeah. Correct. I added in dot c. Yeah, correct. Thank you so much. So now I am corrected here. So let me just write here it is. So y will be equal to c bar dot ab plus plus a plus b whole bar plus c, and then the whole bar. So y will be equal to c bar plus, using De Morgan's law, ab plus a plus b bar plus c whole bar, y equal to c plus, again using De Morgan's law, it will be a plus, so y will be equal to, now using De Morgan's law, it will be equal to a, what happened, a b bar dot a plus b bar plus c bar, right? So if no, I made, yeah. No, I think I made a mistake here. So it is c plus a plus b, a b plus a plus b bar plus c, correct? And then it's a plus b bar plus c plus a b whole bar, and then c bar. Okay, what we can do here is, since we have a liberty of taking, let me just write here, c equal to 0, that implies, given in the question, y is equal to 0 plus ab plus a plus b whole bar plus 0 bar. So y is basically equal to a plus b whole bar plus ab whole bar. So it is equal to y a plus b bar dot ab bar. So it is basically equal to a plus b dot ab bar. So it is ultimately equal to, if you solve it, it is equal to a bar b bar plus a bar b. That is option A. Sorry about that. Actually, I got confused here. So option A, as rightly done by some of you, is the correct answer. Actually, I was trying to solve it further, but since C was equal to 0, that simplified it. That's why. So now the next question is, the gate ideally suited for bit comparison is uh, the gate ideally suited for bit comparison is I even discussed it in the last lecture. So gate usually suited for bit comparison is a two input XNOR gate. So it's a XNOR gate. Basically, when both the inputs are equal, output will be high. So A equal to 0 0 1 1 0 1 1, A B Y is equal to 1 0 0 1. So when they are equal, output is high. So we have an input to a logic gate A, that is 1 1 0 0, and B equal to 1 0 1 0. What will be the output if logic gate is NAND gate? So we have a gate and we are giving these inputs. So A is equal to 1 1 0 0, B is equal to 1 0 1 0, and we have to do the NAND operation. So that is bitwise NAND operation. So NAND operation between 0 and 0 is 1, 1 and 0 is 1, 1 0 is 1, and 1 1 is 0. So it is 0 1 1. That is simply 1 1 1. That is option B. Now, the last question of today's live session is, the number of NAND gates required to implement a function A plus AB bar plus AB bar C is. So I would like you guys to do it first, and then I'll show the solution. So the question asks, the minimum number of NAND gates required to implement a function A plus AB bar plus AB bar C is. Anyone? So let me just show you the solution. So we are required to implement this AB bar and AB bar C. Let's just see, can we simplify it? So taking A common, so it is 1 plus B bar plus AB bar C. 1 plus B bar is 1, so it is A plus A B bar C, right? Then taking A common, so it is 1 plus A B bar 1 plus B bar C. Again, 1 plus something is always 1, so it's A. So now tell me how many NAND gates require. So Y equal to A. Now tell me how many NAND gates require to implement this. Yes, 0. So option A is the correct answer. So I guess that was all for today's live session. We'll meet next week from 3 p.m., where we'll be discussing problems related to combinational circuits like decoders, multiplexers, and other stuff. So that was all for today's live session. Thank you guys for joining. If there are any doubts, okay, maybe there is a doubt. Yeah, go ahead. Any doubt? Someone raised the hand. Sir, does the usage of pull down? So I gave you the hint. It has to do with passing of strong 0 and strong 1. No, it does not depend on that. Basically, what happens here is, if you use NMOS to pull down network, basically in pull up network, you want VDD to be connected to the basically output to connected to the VDD. But what happens in reality, it doesn't. completely pull the output to VDD. It pulls it to some value that is known as VDD minus VTN. This VDD minus VTN drop occurs and it's not completely able to charge. Basically, there is a capacitor at the output. We call that load capacitor. We have to charge that to the VDD, that is the 1 or to 0. So when output, when this thing, when if I put NMOS, PMOS, NMOS here, I won't be able to put V0 to VDD. I will be only able to charge it to some value VDD minus VTN. Not only that, it also decreases the charging of output to VDD minus VTN. Also, charging rate also decreases. So I mean to say, charge it becomes a slow operation. And if you put PMOS in the bottom, it won't be able to completely pull down the output to 0. So it will be only able to drag it to the value mod of PTP. So there will be still some voltage left. So for so that's why we say that NMOS passes a strong 0. So what that means, NMOS is able to completely able to discharge the node to 0 ground, and PMOS is completely able to pull up the node to VDD. That's why strong 1, passing of strong 1, and passing of strong 0. I think these things you'll cover in this digital integrated circuits stuff, and also once we have some basic knowledge of digital, sorry, analog and electronic devices, this is a relatively easy topic for you guys. I hope you got the idea, right? So if not, if there are any further doubts, please let me know. Otherwise, we can close the session. Okay, thank you guys. Thank you for joining.